Texture animation allows us to bring life to objects which would be otherwise static and lifeless. They allow us to create effects such as dynamic projectiles, waterfalls, and portals. Before I explain how they work, we'll first look at the class that is used by this system, the vertex buffer. The vertex buffer has strings for identification, material name, texture name, and surface name for the associated shaders. It holds a pointer to the associated model. The vertex buffer has pointers for the positions, normals, texture coordinates, and tangents of the vertices that comprise a 3D model. These are dynamically allocated when a model file is loaded. The GeoIndex allows the vertex buffer to refer to other vertex buffers which may have the same geometry but different textures or materials. The transform index refers to the transformation matrices that are being used. Material locations refers to the addresses of material variables in a pixel shader and is an artifact of a period when I was using Phong shading for all models. The rest of the variables are self-explanatory. The texture animation class has a pointer to a vertex buffer that it will control. The texture coordinate delta specifies the distance between frames of animation. The start coordinates variable is for storing a copy of the initial texture coordinates of models that are more complex than a simple quad. The animation coordinates store the coordinates of each frame in an animation which is rendered on a quad. The frame delay variable represents the ratio between the frame rate of the game and the frame rate of the animation. For example, if the game frame rate is 60 per second but the texture animation frame rate is 30 per second, this variable will be 2. The update count counts the number of frames that have passed in order to know when to update the animation frame in respect to the frame delay. The initialize function is for interchangeable animations that play on a generic quad. It sets the number of frames, frame rate, and loop boolean of the first element of each array. It calculates the frame delay, then sets the vertex buffer pointer and texture ID. It then calculates the texture coordinate delta based on the number of frames. Next, we calculate the animation coordinates and then set up the initial texture coordinates for the quad just below. The initialize complex function records the start coordinates for models that are more complex than a quad, such as those created by an artist in 3D modeling software. The play forward function first determines the update count. The update count uses the modulus operator to determine when it should update the animation frame. For instance, if the frame delay is 6, which implies the animation is running at 10 frames per second, the modulus operator will return 0 when the update count is 6. We then check whether there are still frames to play by multiplying the frame delay by the number of frames and seeing if it is more than the update count. If the if statement returns true, we update the texture coordinates to the next frame and update the current frame integer. If this animation is set to loop and we have displayed the last frame of animation, we reset the update count and current frame back to 0. The next part of this if-else-if statement checks whether we have another animation to play and, if so, resets the variables and updates the texture coordinates to the first frame of this next animation. The play forward complex functions follow similar logic to the previous function, but updates the texture coordinates one by one for artist-created models. Loop unrolling, simmed, or updating the texture coordinates in a pixel shader are 3 potential methods of optimizing this. The play reverse function plays the quad-based animation backwards. The set animation frame and set current anim allow the frame and animation to be set explicitly. The set state function sets the variables depending on whether the animation is playing forward or backwards, and make sure that the vertex buffer is set to visible. The update functions call the play functions according to the current state. Texture animations use no special shaders because all the important work in this example is performed on the CPU. Any shader that uses texture coordinates will do. In the next example for flow maps, I'll show you how to update the texture coordinates on the GPU. A flow map is a texture that dictates the direction of flow for another texture. This is useful for simulating rivers or waterfalls. Here is an example of what a flow map looks like. In the OpenGL client, we attach the flow map texture as a secondary texture. We pass in a uniform that holds the elapsed time. This will allow us to cycle through the flow. The cycle time is 1 second. In the pixel shader, we calculate the time cycle by subtracting the integer part of the elapsed time from the whole part using the floor function, which rounds out the float. To calculate the flow direction, we then add the time cycle to the S component of the texture. We minus 0.5 and multiply by 2 to keep it in normal texture range, between 0 and 1. We then calculate the color of the fragment by using the albedo map and the flow direction as the texture coordinates. We add the speed multiplied by time to progress the flow for every frame.